Good morning and welcome to the CABE webinar Wednesday. Today we are looking at Introduction to Heat Networks and Heat Interface Units with Lance Colwyn from Vital Energy. This session will cover HIU design, operation, maintenance and compliance, giving engineers, consultants and energy professionals the tools to optimize performance and deliver smarter, greener energy solutions, gain practical insights, enhance your technical know-how, and stay ahead in the rapidly evolving energy landscape. My name is Zaina Kennedy, and I am the Training and Learning Coordinator here at CABE. I will be acting as moderator for this morning's session. CABE strives to create interactive webinars, and if you are watching, then you can join the session live using the Q&A function to submit questions which will be addressed at the end of the session. You are also welcome to contact us at webinars@cbuild.com. Let me now introduce you to today's webinar presenter, Lance Colwyn. Lance is an experienced and results-driven professional with over 36 years in the controls and HVAC industry. He is currently leading the HIU and CIU business unit at Vital Energy. He has a proven track record of delivering complex technical projects, driving product innovation, and leading high-performing teams. So now I will hand over to Lance to begin the presentation. Over to you, Lance.
Thank you, and good morning if you're from the UK, or hello for everybody else. As we've mentioned, my name is Lance Colwyn and I am from Vital Energy. So, very quick one, a few learning outcomes. We're going to talk about the different terms describing different heat networks. We're going to go a quick overview regarding heat interface units, HIUs. How we get the most out of our HIUs. So we'll be looking at performance and then key regulations and key regimes. So one of the things that I'll start off with is a quick introduction. I'm Lance Colwyn, as I've said. You can see my contact information. Our CPD is approved both with CABE, of course, and also CIBSE if required. And I will leave that up for just a little bit longer. If you do want to see my LinkedIn profile, if you click on the QR code, you can get hold of me. And also if you want to get hold of me after the webinar as well. So a little bit about Vital Energy. We have over 30 years dealing with district heating systems, and we have 7 offices based all around the UK, so up in Glasgow in Scotland, Newcastle in the northeast, our head office here in Blackburn, which is also our HIU manufacturing facility. We have an office at our Drayclough Energy Centre, London office to cover down south. Our Hereford office also deals with our heat pump systems, and a small office over in Swansea. As you can see very quickly from some of our vital statistics, we have quite a lot of graduates. Most of our fleet are either hybrid or electric. We have various accreditations. We've got over 200 kilometres of district heating pipework. We're nearing more to 100,000 homes now connected with various projects for heat pumps, solar and energy conservation. One of our latest ones is over at Lancaster University, Swansea Hospital with solar and so forth, and also energy plant. And then we've got various awards, and we're now nearing to around about 800 employees nationally, and that is increasing on a day-by-day basis. The idea over the next 3 years is to carry on expanding that to around about 1,400 employees. And of course, our turnover will increase as well. So what's our technical capabilities? So very quickly, I will blitz round. So we'll deal with anything from energy sensors. That could be waste to heat. It could be boiler. It could be heat pump systems. Our heat network, so all the underground pipe work, and we'll go into that in more detail. HIUs, heat interface units, cooling interface units, and also any metering that is required. Energy storage, so battery storage facilities, solar PV and renewables, so large solar farms. It's not your individual house one, but it's large scale. And then, of course, energy conservation measures. So we're talking about our ESCOs, where we would probably deal with anything for 20, 30, or even 40-year ESCO facilities. One of the things we also have here, which was developed during COVID, funny enough, and built during COVID, is our new training centre. And here we actually recommend that all HIUs and CIUs are commissioned by competent engineers. And we actually run our own in-house and for external companies, engineers to actually undertake that training course. We don't charge for the course, but what you will have to do is, if you are coming from Blackburn, you'll have to pay for your own accommodation. And we do sometimes tailor some of the courses depending on engineers' requirements as well, if need be. But normally we have a core element that we run through. So that will involve some PowerPoint presentations to get some learning information. It can be then going on to the practical, where you'll actually service, look at servicing and maintaining and fault finding on HIUs. So let's start with heat networks. So there has been, we're up to the 5th generation of heat networks. So if we start with the first generation from 1860s, you're looking at steam, and you're looking at up to 200 degrees with no pump circulation. Going to the 1930s, we're now starting to circulate that water around, but we're now bringing the temperature down to around about plus 100 degrees, but we are looking at 70 degrees on the return pipework coming back. Going to the 1970s, where we're into our 3rd generation, we are circulating the water, but now we are starting to try and bring down both the flow and the return temperatures on that flow and return pipework. Going into the 4th generation, where quite a lot of networks are at the moment, and we're now looking, bringing it even lower, and we're introducing now at this point, not only just the gas boilers, but we're also bringing things like waste to heat, biomass, and the start of heat pumps. We're now into the 5th generation, so from around about 2020, and the idea is now we are starting to bring in ambient loop heat pumps and also bring the temperatures even lower. So we're now at a point where we're up to 60 degrees, 55, 60 degrees on the primary flow, and the return temperatures at around about 30. The reason for ambient loop heat pumps is we can now look at things like utilizing summer cooling as well. So we'll move on. So let's start with our first network. So we call that the community heating. And one of the things that you can see by the picture bottom right-hand corner is our community hub. And that's a heat pump basically in a container that can then go to a new housing estate, and maybe up to 80 properties. And therefore this works out at a lower cost, more efficient way of doing it, instead of each house having an individual air source heat pump. One of the main things is things like actually powering all those individual ASHPs instead of one centralized plant. So we can therefore help reduce, especially on small local housing estates, but also if you don't have the adequate access to the grid as well, we might be short on grid accessibility. So we then talk about communal heating networks. And as you'll see, it could be going from a community hub, it could be anything, it could be gas plant, it could be biomass, it could be a mixture of all different things. But one of the things that you'll see with a communal heating network, maybe that's the boiler system or your system down in the basement of an apartment building. It could therefore be requiring and consists of risers going up, that's your pipework going up your building, and laterals going across. One of the things that is now coming into effect is what we call CIBSE CP1 Objective 3.9. And what that talks about is that instead of having a single riser and very long laterals, we're now talking about that you have a requirement now for multiple risers going up and down the building and shorter laterals going across the building. One of the projects that we were involved with was the pipe fitter thought he was doing a really good job where he did the laterals going across the ceiling, but there was columns along the ceiling. And what he did was he went across, down, around the column, up, down, and he actually caused more problems by actually causing air to get trapped in those laterals going across the building. It also helps with not having things like dead legs and things like that as well. So we say no to single risers and long laterals, and now we say yes to multiple risers and shorter laterals. So let's move on now to district. So district heating schemes, there you might have your energy centre. That could be waste to heat, it could be gas, it could be bio, it could be a multiple of elements. And then you've got your underground pipework, which will then be feeding all the different apartments, buildings, it could be government buildings. So if we then look at that, and I'm about to show you a video, one project that we have been involved with is over at Leeds City Centre. So,
Pipes project is the installation of district heating infrastructure stretching across the whole of Leeds. The Leeds Pipes network is pipes that takes heat that's currently going up the chimney of our waste incinerator and uses it to provide heating and hot water for businesses and homes within the city centre. The Leeds Pipe project is bringing cheaper energy to 1,440 properties within the Leeds area. Benefits for the City of Leeds for the district heating scheme is reduced carbon emissions for the area, improved air quality, and reduces fuel poverty. The project's been successful because Leeds City Council and Vital Energy work together in an open, honest working relationship, clear communication, involving all the stakeholders from very early on. That's made it successful to date. We have an ambition to become carbon neutral by 2030, and by being able to do things like this, which is using existing sources of heat that will be going to waste to actually heat commercial buildings and homes across the network, it really does make a contribution to reducing our impact on climate change. It's really important as an organisation like the Playhouse, which is deeply embedded in its community, to think about future generations and our carbon emissions. It's now that we should be making lead steps to make this actually happen.
So hopefully that's given you a little bit of an insight of what a district heating scheme portrays and looks at. And as I've mentioned, with communal networks as well, we've still got risers going up the building and laterals coming in. But what we're now also introducing is also the tertiary system. So a HIU, therefore, will be that barrier between the riser coming up, what we call the secondary system, and the tertiary system, which is your radiator system, your underfloor system, and your domestic hot water. So one of the other projects that we've done involving a district heating was Queen's Quay up in Scotland. And what that's done is it's actually taking the water content out of the River Clyde, and that's actually going to 2.65 megawatt high temperature ammonia heat pumps. It's also backed up with 2 7 megawatt resilient gas boilers, and we've also future-proofed that. Also, there is over 1,200 homes that are being fed, and they all have their HIU, their heat interface unit, inside their apartment, and that's then feeding their radiator circuit or their underfloor circuit, and of course domestic hot water. This is then also coupled with a metering solution. We call it the Glass Communications app, and that can either be on an app actually on your phone or on a small in-home display, a bit like a smart meter. So we're going to now move actually and talk about heat interface units, HIUs for short. So what is a HIU? Well, it's a way of providing control. We'll be looking at metering, and therefore the end user can therefore see what their bills might be. They're also known as heat stations, hydraulic boards, or hydraulic interface units. Normally hydraulic interface units could be either heating or they could be cooling. But for this purpose, we're going to just be talking about heating HIUs. HIUs provide instantaneous hot water and also indirect or direct heating. Why do we use them? Well, we want to have that hydraulic break, and we're also looking at the various temperatures, because communal or district networks could be 70, 80 degrees, and you don't want that flowing around, let's say, your underfloor system, where you're only looking at 45 degrees C. Also, one of the main benefits is that we are now removing any requirement for gas installations. And let's face it, in high-rise buildings, gas can be quite problematic. One of the new things that has now come out is the new British standard, BS 8635-1, only came out last year, and part 2 will be coming out probably towards the end of this year, stroke next year, and that will involve HIU installations and give all the relevant information that is required for installations of heat interface units. They've now made the criteria smaller. So if we talk about things like space heating, so you've got going through an indirect heating plate heat exchanger. It might be direct with mixed down or basic control. You've got your domestic hot water, DHW, where normally this is instantaneous, where we do go through a plate. So we've got that segregation barrier. It could be that it's going to a domestic hot water cylinder or some form of small thermal store. And then if we do talk about cooling units, again, we have either indirect or direct cooling units. The difference is indirect is going through a plate, therefore you've got that barrier, and direct means it's got some form of mixing from the primary circuit. One of the things that's also been introduced is a naming convention. And if you have a look on our brand, as an example, we had 3 versions of our HIUs. So if we go back, we had the original thermostatic ones where there's no electronics controlling them. We have hybrid ones where the domestic hot water was electronically controlled. However, the heating part of it was thermostatic controlled. But now we have moved fully into fully electronic HIUs and CIUs, and therefore we've now called our branding vTherm E for electronic, and we are therefore changing everything to conform with the British standards. And the naming convention, as you can see in the middle, is we've got HI for heating indirect, or HD for heating direct, either via a plate or directly. And again, cooling indirect going through a plate. And then of course, hot water, domestic hot water, always indirectly going through some form of plate heat exchanger. And because we build both copper HIUs and stainless steel HIUs, we're then including the prefix C for copper and S for stainless steel. And I'll go into a bit more detail regarding the differences as well. So, how do we control HIUs? What do HIUs or heat interface units look like? So originally we had, as I've mentioned, the thermostatic heat interface unit, and therefore they would have had control valves. And as you can see, those valves would have had a capillary going to some form of head, and that would then dictate the temperature that would control at. And in most cases, both the heating circuit and the domestic hot water would operate at the same time because these were quite large and bulky. And now we're moving away from that. And one of the things is we're looking at electronic heat interface units. So these are now electronically controlling the control valves. In most cases, we're looking at some form of pressure valve, pressure independent valve, differential pressure control valve, and we get a better control. Also, we can look at additional functionality. So one of the things that we do with our electronic HIU is we exercise the pump every 25 hours. Why do we do it 25 hours? Well, if you did it at 2 o'clock in the morning every 24 hours, your subconscious sleeping mode would actually hear that maybe that pump just turn over for a few seconds. And we can look at things like fault codes, and we can look at monitoring functions and so forth. And then we have hybrid HIUs, which are being phased out, where I've mentioned that we would have had some form of thermostatic control on the heating. We would have an electronic control valve on the domestic hot water, and that is to help improve the domestic hot water response time that's required to meet BESA testing requirements. And one of the things at the moment is that people are finding it hard, especially with thermostatic HIUs, to actually pass the BESA regime. So things like modification to the regimes are needed to help thermostatic HIUs be compliant. So while we're talking about the British standard, very quickly, you can see that's the symbol, and we're looking at indirect heating, but with instantaneous hot water. So therefore, what we commonly known as a twin plate HIU. And you'll actually see that we're having anything on the primary side of the HIU up to 16 bar. And we've got temperatures normally in the region of between 50 to 90 degrees. Commonly, I would say that at the moment is around about the 70, 80, but we do get quite a lot of inquiries now for approximately 60 degrees on the primary side. We're looking at anything up to 70 kilowatts on the domestic hot water and up to 20 kilowatts of heat on the heating output. And of course, because it's on the secondary, on the heating, we'll be looking at normally controlling that at around about the 1.5 bar. But there are pressure relief valves actually in the HIUs that trigger at 3 bar if anything untoward happens. And as you can see, our standard twin plate here is up to 70 kilowatts. It's been BESA tested, and we're getting anything up to 10 kilowatts of our heating output. We're controlling via pressure independent control valves, PICVs, and we have our unit in an EPP case, and this helps to stop heat losses. EPP, for anybody that needs to know, it's expanded polypropylene, and there is justification to use that instead of a metal case, and then you have to then start insulating all your pipework within your HIU stroke CIU. And as you can see, the HIU will actually fit within a standard 600 by 900 kitchen cabinet if need be. If we now look at a single plate HIU for the domestic hot water, we've now got direct heating. And one of the things there is, because we're now part of the primary circuit, the pressures now are been reduced to 6 bar on that primary, because let's face it, you don't really want 16 bar going to your radiators and somebody decides, oh, I think I'll decorate and pull their radiator off the wall. So we've got to therefore bring these pressures a lot lower to stop flooding and so forth. And as you can see also, we're looking at anything up to 60 kilowatts on our unit. Again, 10 kilowatts on the heating. The difference now is that they are being controlled by a differential pressure independent control valve, and that has some form of capillary that then joins between the primary and the heating circuit that is leaving the HIU to therefore be able to monitor that differential pressure. We then also can deal with indirect domestic hot water HIUs. And domestic wise, again, you're still looking at around about the 70 kilowatts. We do bespoke domestic hot water only units, again, in the same enclosure, and we can go up to around about 200 kilowatts. Again, it all dictates on your primary temperatures as well, that kilowatt rating. One of the also things that we've started to introduce is, you'll see on the top of the HIU, instead of having internal strainers, we're now looking at isolation valves with inbuilt strainers as well. So that's something that's quite unique to ourselves at the moment. And our new HIUs and CIUs will all be coming out with that technology. And then we also do heating only HIUs, as you can see, HI-1. Again, we're back to the 16 bar on the primary because we're going through a plate, and normally we're looking at 20 kilowatts. And this is indirect to the tertiary, i.e. your radiator or your underfloor system. And again, our unit, as you can see below, is up to a 24 kilowatt unit and is controlled again by PICVs. We then do indirect cooling units as per the British standard. And again, these are normally smaller units, and normally you're looking at 10, maybe 20 kilowatts maximum. Again, it depends on the control that you require, and also your differential temperatures with the approaching and offset temperatures. So the cooling is actually quite hard to control, and therefore certain parameters are required. One of the things that we've done with our HIU is we keep them separate. We don't combine them like other manufacturers may do. That has two effects. Number one, HIU is around about 35 kilos. CIU could be 45 kilos. And if you have that as a joined unit, you've got a lot of weight there to try and install, first of all. Also, the pipe work is being blended together. The other thing is, you're then restricted where you can mount HIUs and CIUs. So if they're separate units, you can put them top and bottom, side by side, or even in different locations altogether. So let's talk about the operation of HIUs. So if we start looking at the components within a HIU, and on the left-hand side, you can see one manufacturer, on the right-hand side, another manufacturer. And one of the things that you'll see, main difference is one has top entry pipework and one has bottom entry. Both don't matter because normally you'll have some form of bracketry that you can pipe up. You can stand HIUs off the wall with a bracket and therefore bring pipework downwards or take pipework upwards. There's all different flexibilities, so it really doesn't matter, especially with new builds, what you're doing. Retrofit, as I say, you could have a bracket. If somebody's already had pipework, we get asked to make our brackets taller in some cases to help with retrofit projects. But let's talk about the actual components. So first of all, you can have some form of electronic controller. Some have displays, some don't. We'll then talk about the expansion vessel, therefore on your heating circuit. You'll have your plate heat exchanger and of course some form of control valve to actually control that. You'll have your heating plate with its control valve. And in some cases, because manufacturers are just using a standard controlling valve compared to other manufacturers like ourselves that use pressure independent control valves, they therefore will need a separate additional differential control valve is required to help with that regulation as pressures are up and down within the circuits. Standard heating pump, therefore, to circulate the heating circuit, and also a heat meter. This is therefore to give you your kilowatt output and other information, maybe temperatures. That could be interrogated by a third-party product, or in our case, we also use our own in-house product, the glass, as I've mentioned before, and therefore you can get all your metering information and also help with billing as well. Your pressure relief valve. So again, if the heating circuit goes above 2.5, 3 bar, that pressure relief valve will then release. We have a safety valve. So the safety valve is a electronic or mechanical spring returning to tight shut-off valve. And this is used if you think of, let's say you're having a shower and suddenly power is lost to the HIU, the controlling valves suddenly stop where they are. You could therefore cause a scalding issue. So the safety valve actually shuts the primary circuit down, and therefore, worst case scenario, you get a cold shower. And in some cases, the safety valve can also be doubled up, and that can be used also for as a prepayment valve as well. So it can have a dual functionality. We've then got the mains cold water flow sensor. That's normally some form of turbine or maybe an ultrasonic sensor. And therefore, that's what triggers the heating demand, hot water demand, and therefore starts that cycle. And then you might have a temperature gauge, pressure gauge, or it could be that it's being displayed on your electronic controller. And then we've got various drain and fill valves. Very quickly, we've then got the primary circuit, flow and return, your CH or your space heating pipework, flow and return, your mains cold water coming in, maximum of 10 bar, and your domestic hot water, hopefully nice hot water, flowing back out. And then, as I've mentioned before, the safety relief valve discharge pipe. And one of the things, as I mentioned, you'll see on this unit is compared to the one on the right-hand side, we've now got filter valves. So where we would have had to drain down a HIU to clean the filters out, and this is quite common in the industry, one of the things we've now developed is these filter isolation valves. That means when we isolate, we only now remove a thimble amount of water, and that also helps when we do introduce it back into the system after we've cleaned. We're not adding air, which is bad for the system, and also we're not weakening any inhibitor water as well. So let's talk about the actual physical operation. You'll have some form of either an app or a electronic thermostat, time clock, scheduler, and that will therefore enable the controller to go, right, I've now got my time clock, I've now got my stat to say, oh, I need heat. And therefore that will then trigger the electronic controller to, number one, bring on the pump, and number two, control the controlling valve. And therefore, there are typical temperatures that you would then see circulating and returning back from the system. And also with it being electronic, as soon as it's finished the heating demand, the pump will do a pump overrun as well. Something that's different compared to thermostatics sometimes have the issue, especially when you come from the summer months to the winter months, where the pump suddenly is seized because it's had no pump exercise as well. So what reasons will we be having for high return temperatures? So if we look at no flow, this could be from pump failure, water quality, or air in the system. And therefore you can see there's different colouring of water content quality. Ones where the inhibitor has been mixed with the actual flushing fluid originally, and the other one has had no inhibitor, and you can actually see where it's taking rust from all the different pipework. The other thing you'll notice is there's lots of air in the system, and again, that's a detriment. If we have uncontrolled flow, that's normally from an unbalanced system, where it could be your lock shields on your radiator valves haven't been set or have been set fully open. But also one of the main things is people put the wrong type of heads, and different heads will have different flows selected on those valves. So one of the things is you've got to make sure that you've tied your head with your control valve. So if we then start looking at the domestic hot water, one of the key functions is the keep warm function. And on there, we're looking at having a temperature around about 40 to 50. And what you'll get is an effect where we want the plate to be nice and warm, ready for when the tap is brought on, because BESA says that we have to have at least 45 degrees within 15 seconds. So as we bring the tap on, we will get a domestic hot water requirement, because from the flow turbine, that will then start controlling the control valve and actuator, and therefore typically you'd have nice hot water flowing out at 50 to maximum of 60 degrees. 60 is normally for NHS applications, 50 to 55 is common for domestic, and then of course you'll have anything maybe up to 20 degrees on the return. So let's talk about regulations and test regimes. So we've quickly mentioned about BS. I'm going to quickly go over BESA, CPD-certified we've already mentioned, HSG 274 Part 2, which is also part of Legionella, the new off-gen regulations, and a little bit of a HENTAS. Our HIUs have either been RAS or KIWA Reg 4 approved, as well as BESA tested, and we're also partners with NBS Source, and we're also part of MENA, the Manufacturer Equipment for Heat Networks Association, and so forth. So we've already done an overview of British standards, so I'm not going to go into too much detail, but very quickly, indirect, direct, and instantaneous hot water systems, domestic up to 70 kilowatts on the domestic hot water, up to 20 kilowatts. Depending if we are direct or indirect, it might dictate if we're up to 16 bar or 6 bar. And again, the same thing with cooling networks and domestic hot water. You need at least half a bar and no more than 10 bar on the mains cold water. One of the other things that we've also looked at and we've got approval on is we've dealt with our HIUs for low voltage directive, and also EMC, being EMC compliant, and also check to make sure our sound levels meet ISO 3744. That is to make sure that people can actually sleep and your HIU is actually nice and quiet in its operation. Not all manufacturers have undergone this, so just be aware of that. So BESA testing 2023. If you actually scan that QR code, you can actually go to the BESA website and it actually goes to the results of our HIU. But you can see other manufacturers as well. But we'll go into a quick overview regarding it. So HSG 274 Part 2 and Legionella talks about making sure that we've got adequate flow and return circulation. We've got to make sure that hot water meets the required temperature requirements, and cold water must be below 20 degrees. So therefore, we're not going into Legionella risk. And of course, part of that is that we conduct a Legionella risk assessment. So building owners got to make sure that they have had a Legionella risk assessment associated for that. We need to make sure that things like all our pipe work has been cleaned and everything is disinfected requirements. And we've got to make sure that we can monitor temperatures, look at biocide levels and so forth, and do the appropriate sampling. And of course, along the way, you've got to make sure that you maintain detailed records of everything that is maintained and inspected as you're going along. So, Ofgem. Originally, HIUs and heat networks and so forth did not fall under Ofgem. So one of the things that is happening now is that as of now, we are moving into where we've got different phases, and Ofgem will be like you have with your gas and your electric, will be fully compliant. And as you can see, there's some timelines of between the initial phase where we are at the moment, going into second phase, which is starting early next year, where you will actually have to register your networks. Going into fully operational phase 3, and we're only talking about, in a few months' time, authorization conditions actually kick in and regulations are being enforced to help with consumer protections, making sure that they're not paying silly bills and making sure everything is compliant. And this now will be carrying on with the transitional period to approximately 2028 as well. So what does it mean? It means to address the imbalance and monopolizing between operators and consumers. We've got to make sure that bills can be paid, and also where heat networks are repaired within a reasonable time frame. And if you're in the UK, England, you've got the Citizen Advice Bureau, and you've got Consumer Scotland if you're in the north. And of course, you can then look at going through Ombudsman services to make sure that if you do have any complaints, there is now a process there, similar to gas and electric as well. That's a quick heat network regulation map. So again, as you can see, there is an ongoing activities. And that, as a quick overview, we'll talk about the HENTAS, rapidly growing heat networks, because there's thousands of them. And also one of the main things is under HENTAS are the 26 key performance indicators that will be required for new projects to be compliant. And as you can see there are different phases of the HENTAS assurance scheme. So, beta testing. We're going to talk about BESA 23 because that is the current standard at the moment. There will be shortly a BESA 2025, which is going to be very, very similar with just a few little tweaks. But basically, the difference between the old BESA testing standard from 2018, because of COVID, there wasn't 2021, are a few items. So we've now made it modular. So they can now perform different modular tests. So if you've got a heating only, you'll do just the heating only requirements. If it's domestic hot water, you do the hot water only. And if it's both, then you'll do, again, all the different modules required. We've now changed the temperatures. So we've now brought the low temperature to 55 degrees, as well as the high temperature testing at 70. And one of the other main things is, apart from the modular element, is that we're now testing at both half a bar, which was the originally, and now 2 bar tests. And also you'll notice on the right hand side of the display, we've got best practice elements as well. That doesn't stop you from achieving your pass on your modules, but we are trying to push the industry to make better and better HIUs to have those achievements. And as you can see on the left hand side, you'll see where it's got primary differential pressure. You can now see that the tests are now being done at half a bar, then it jumps, and you can see that by the pink lines going up and down. And they are the tapping tests. Again, as I've mentioned, they are now both done at half bar and 2 bar pressures. If you remember, I spoke about the domestic hot water keep warm cycle, and as you can see, it will start at, let's say, the temperature within the HIU plate has dropped down to 42 degrees, 44 degrees, and then it'll get a blip, maybe 10% open of the valve. That will then heat it to the 50 degrees, and then it'll gradually degrade again over time. One of the key things there is what that degrade time is. On this particular unit, our unit, we're talking anything between 32 and 42 minutes. Other manufacturers could be low as 6 minutes. And therefore, you could be talking about excess usage of that valve actuator and therefore reduce the lifespan. So just be aware of that. Here you can see by the red dotted line, we've got a sudden spike. This is the purge, which flushes the primary pipework out. And this helps with the speed up the domestic hot water reaction time. On this particular graph, you can actually see, I'm just checking on time, we're not too bad. You can see here different flow rates, but again, you can see that we now do the test both at half a bar and 2 bar. And again, you can see with the heating tests, again, we've now changed the test. So originally it was 1, 2, and 4 kilowatts. We've now brought a new test, so it's now harder. So we've got a half kilowatt, 1 kilowatt, and 4 kilowatt, but the 1 kilowatt now is now done at that 2 bar test. So if we look at the different manufacturers that currently have tested to BESA 2023, one of the main elements is that you want to look at the lowest VWAT of the HIU. So if we look at that, but also another key element that people want to be aware of is the annual volume. And very quickly, you can see the different volumes, and other manufacturers have 30 VWAT of 30, and then they're gradually creeping up. If we look at the next one, done at 70 degrees as a prime example, again, because you've got higher temperatures, therefore the VWATs is lower, and you can actually see, number one, our unit has been tested to 70 kilowatts, and we've got the lowest annual volume. So if we took the top two, so if you have a look at, as an example, we've got a VWAT of 24, and we've got a standby volume of 15.6. If we then look at the nearest one, which is the third one down, you'll see that the VWAT is at 25, but their standing volume is now at 20.6. So now we've got a difference of 5 meters cubed per annum. If we now look at, maybe we've got 1,000 HIUs on a building complex. That's now 5,000 meters cubed an annum that you've got to circulate around. If you now convert that to litres, as an example, we're now talking about 5 million litres per annum needed to be pumped around the system. And a typical lifespan of a HIU of, let's say, 15 years, we're now talking just extra circulating around standby volume. We're now talking about 75 million litres that's required over the lifespan of that HIU. So it is really critical that you size and get the right HIU for the right application. HIUs might be a little bit more at the beginning of a project, but over the lifespan, and for the consumer, there could be big differences. So what we learned. So very quickly, we've spoke about the 3 different networks: community heating, communal heating, and district heating. What are the different HIUs? So we've spoke about them being known as heat stations, hydraulic boards, hydraulic interface units. There was 3 types: thermostatic, hybrid, and electronic. And how do we get the best out of them? We want to look at optimizing the performance. We want to make sure they've been designed correctly. So you can look at things like BISA and BISRIA requirements, how they've been installed. So we're looking at risers and laterals correctly, and making sure that they've been commissioned. Some manufacturers will only do a 10% commissioning, and then the rest is online. How do you see if the wiring's been done correctly? How do you see if you've got a small leak on a HIU if you're doing it remotely? So we always recommend it should be 100% on-site commissioning. Making sure that water quality, making sure the systems are balanced and they're regularly serviced. Again, some manufacturers are 1 year, some are every 2 years. And then making sure that we've got adequate and the correct billing. And then, as I've mentioned, the key new regulations and test regimes. We spoke about Ofgem, we spoke about HENTAS and CIBSE CP1. We've spoke very briefly about the BISA testing, the new British standard, low voltage directive, EMC, sound, and of course, last but not least, HSG 274 and CIBSE Legionella. So, again, if you need to scan me, you can do from that QR code, but I'm quite happy to take questions.
Thank you, Lance. There aren't any questions in the Q&A section at the moment. I believe Catherine or Emma have been answering as the webinar's been going along. I can hang about for a couple of minutes if anybody does pop anything in, and then I can read it out to you.
So one of the questions I was asked was regarding what is VWART. So if HIUs can have all different accessories, by the way. So you can have, as I mentioned, the brackets, and we have bypass assemblies and so forth. And one of the questions I was asked before was, what is VWART? So VWART stands for volume weighted average return temperature, and that's how the calculation is broken down for the VWART calculation.
Yeah, I think the questions are being answered via Catherine or Emma. So with that, oh, we've had one come in from an anonymous attendee. What is the smaller end limit in your opinion?
What is the
smaller end limit in your opinion?
I'm trying to work out what they mean by the smaller end. Could they elaborate a little bit more?
I'm hoping they'll hear that and add something else.
If not, if they want to take my details, I'm quite happy to answer an email.
Yeah,
what is
sure.
Smaller end limit in your opinion? Yeah, as I say, it's a little bit limited on what they mean by that small end limit.
So we've had a couple following that from 2 other people though.
Okay.
What is smallest scheme worth considering network for?
Right. Okay. So if we talk about the community network, you know, we could be looking at a heat pump system, and that could be for social housing as an example. And that could be, they call them, instead of apartments, they call them units. So it could be, we've done projects where there's only 10 units as an example. And that's all being fed by a heat pump system, or it could be still from a boiler system. One of the main things is the HIU is there to help as a separator between the primary circuit and your tertiary circuits. And yeah, we can cater anything. You know, we have ones where small quantities, 5, 6, 10 HIUs on a small circuit, to ones that are, I think the largest individual circuit is about 3,000 HIUs.
Brilliant. And then there's another one saying, can the HIU be connected to an underfloor heating system?
Underfloor heating system, yes. So the HIUs are heat pump ready, but also can be working with underfloor, as I've mentioned, and you could see by the slides, both underfloor and radiator. The difference is instead of a time clock thermostat telling the HIU to be triggered to start circulating, the underfloor manifold controller actually gives that, in effect, they call it a boiler demand, but it goes to the HIU, which then triggers the same thing, the CH. The difference is we changed the settings within the HIU to only operate at lower temperatures for underfloor to stop things like cracking of the flooring. And therefore, a typical temperature would be 40, 45 degrees that it's circulating at. And that would then go to the manifold. From the manifold assembly, then that would then trigger. But yeah, if that person wants to have more information, again, contact me and I can run through in a lot more detail, not a problem.
Perfect. Thank you, Lance. We have come to time for the webinar. So if it's okay with you, I'm going to wrap up. We'd like to thank you for presenting and to everyone who has joined us this morning. As a reminder, this session has been recorded and will be uploaded to both the CABE website and our YouTube channel soon, which you can share with your colleagues. With that, I'll wrap things up for today. Thanks again, Lance, and to everyone for
Thank you
taking
all for
part
attending.
today. We will hopefully see you at the next CABE webinar. Take care, everyone. Bye-bye.